Hello students, you are welcome to another edition of Chemistry for S1. I am your facilitator, Richard Gyamfi. In our last meeting, we learned the main group elements, the transition elements, the lanthanide and the actinide series. Today, we are still on the periodic chemistry, and we are going to look at the position of hydrogen in the periodic table. We also look at the periodic law and the periodic properties. Hydrogen is the most abundant element in the universe, and it's the simplest element and a unique element in the sense that it has no neutron in the nucleus. All other elements do have neutrons in their nucleus, but when you talk about hydrogen, it has only one proton and one electron, and therefore is unique in this sense. Where do we place hydrogen in the periodic table? In fact, there is no totally suitable position for hydrogen in the periodic table. Nonetheless, most of the periodic table charts or the periodic table have hydrogen placed in group 1. Why hydrogen is placed in group 1? Hydrogen has one electron in its outer and only shell, and therefore it normally loses the one electron to form plus one oxidation state, the hydrogen ion, which is hydrated in aqueous solution to give the hydronium or the hydrozonium ions. And exhibiting this property, it is qualified or it is placed in group 1 because all the group 1 elements do have one electron in the outermost shell, and they all lose this one electron to form +1 oxidation state. So since hydrogen also loses the one electron to form the +1 state, it resembles the group 1 elements, and therefore it's placed in group 1 elements. It's placed in group 1. Now we've seen that it can be placed in group 1. On the other hand, hydrogen gains one electron to form something called hydride, H minus, like the halogens do. All the halogens gain one electron to form the -1 oxidation state. So hydrogen 2 or hydrogen can be placed in group 7 or the group 17 because all of them form -1 oxidation state by gaining one electron. So in summary, hydrogen can be placed in group 1 and or in group 7 or group 17. These are the two groups by which we place hydrogen. But as I've told you, traditionally, most of the periodic table charts place hydrogen in group 1 because it's an S block element. This is what we see here in the periodic table. This is a chart of the periodic table, and you see hydrogen here is placed in group 1 because of this. And it can also be placed in group 7 or group 17 because it gains 1 electron in compounds like sodium hydride and magnesium hydride. And in fact, all of them do gain 1 electron, and it therefore resembles group 7 elements too. So it can be placed in group 1 and group 17 or group 7A. So that is it. These are the two places hydrogen can be placed in. Now let's look at the periodic law. What is periodic law? If you look at the periodic table, the elements have been arranged according to increasing atomic number. And what we see is that some properties do recur at given intervals, at regular intervals. And it's based on this term called periodic law. It states that the properties of the elements are the periodic functions of their atomic numbers. In other words, it says that when elements are arranged with increasing atomic number, elements with similar properties are grouped together, or elements with similar properties do recur at given intervals. This is what we call periodic law. And it's this law that helped in classifying the elements. But what you see is that when you consider the group 1 elements, lithium, sodium, potassium have something in common. They show similar chemical properties and similar physical properties because of the periodic law. So periodic law can be stated as the properties of the elements are the periodic functions of their atomic numbers. In other words, This is periodic law. With this law, we see that in any group, for example, the group 2 elements, the alkali metals, beryllium, magnesium, calcium, strontium, barium, and radium, they all have similar chemical properties. They have something in common, and it's based on the periodic law. Now, let's move on to periodic properties. What is periodic property? Or what are periodic properties? They are properties, either physical or chemical, that change periodically as atomic numbers increase. They change periodically as atomic numbers increase. And they include atomic radius or atomic size, ionic radius, ionization energy, electron affinity, electronegativity, diagonal relationship, melting point, atomization energy, and so on and so forth. So there are many, and we are going to take them one by one. We'll take them phase one, atomic radius and atomic size. Then we look at the trend. So, periodic property. So any property which changes periodically as atomic numbers increase, we term that as a periodic property. They include ionic radius, ionization, energy, electron affinity, electronegativity, atomization, energy, melting points, etc., etc. So that is periodic property, and we are going to take them one by one. Today we'll be able to, I'm sure we'll be able to look at atomic size or radius, and if time permits, ionic radius too. So we are taking the first one. Atomic size or atomic radius. What is atomic size? What is atomic radius? In fact, if you consider any atom, the electron cloud extends infinitely, and therefore the atom or the atoms do not have sharp edges, and it becomes difficult to locate the boundaries. Therefore, it's appropriate that we measure atomic radius instead of atomic size. However, the two terms are used interchangeably, but we look at atomic radius instead of the atomic size because of what I've given you. What is atomic radius? It is 1/2 the distance between the nuclei of any two closest atoms or adjacent atoms. It is one half It is 1/2 the distance between the nuclei of any two closest atoms. We have two forms for the this atomic radius. If the substance atoms in a substance if the substance is a molecule, then we are going to have a covalent radius. And if the substance is a metal, then we have a metallic radius. With the covalent radius, when the atoms form the molecule, the orbitals overlap, and therefore we have something like this. So this is the metallic radius. Here the orbitals do not overlap. Here, this is the nucleus and the nucleus. So the distance from here will be the T. So here will be the radius. How is the atomic radius measured? It is measured by electron diffraction or X-ray diffraction or the infrared spectroscopy. With this, we can measure the ionic radius to give the atomic size or the atomic radius. I've told you that these terms can be used interchangeably. We can say atomic radius or the atomic size, but I've told you it's more appropriate to use the atomic radius. So atomic radius is measured by electron diffraction, X-ray, or infrared spectroscopy. These are the means by which we measure atomic radius. Now let's look at the trends of the atomic radius across a period and down a group. The trends in atomic radius, whether it increases or decreases, moving across a period from left to right or within any particular group. Trends. In atomic radius or size. Whether this increases or decreases across a period depends on the effective nuclear charge and also the screening effect. If you remember, in our previous lessons, we learned the effective nuclear charge, which is the net positive attraction or net positive charge the outermost electrons feel or experience by the protons in the nucleus. You know, there's an attraction between the protons in the nucleus and also the electrons. So the core electrons always reduce the kind of force being exerted on the outermost electrons. So after the core electrons blocking the force or the attraction being exerted by the nucleus or being exerted by the protons in the nucleus to the outermost electrons, so the remaining attraction or force that gets into the valence electrons, the outermost electrons, is what we call effective nuclear charge, and it plays a role in determining the size or the radius of the atoms, and also the shading or the screening effect, which is the reduced electrostatic attraction between the protons in the nucleus and the valence electrons. So these two factors determine whether we are going to see a decrease in atomic radius or an increase in atomic radius. When you consider the arrangement of electrons in the periodic table, if you're moving from left to right, whether we are going to see a decrease or increase depends on these factors. The factors that determine the size of the atoms in the periodic table include the following. Effective nuclear charge and shielding effect, which is also called screening effect. So now let's consider the periodic table moving from left to right and see whether the size is going to decrease across a period from left to right or within a group. If you look at the elements, let's take the period 2 elements, lithium, beryllium up to neon. They all have 2 subshells. So lithium, the atomic number is 3, so we are going to have 2, 1, meaning we have 1 electron in the outermost shell. Let's consider the electron in the same period, the farthest, the neon, which is 10. We're going to have 8 electrons in our outermost shell, and the electrons that come between the nucleus and the outermost shells are what we call core electrons. I hope you remember. We did it in our previous lessons. So here, the shielding remains constant. The core electrons are constant, or we have 2 electrons doing the shielding. But the nuclear charge is increasing, and when the nuclear charge is increasing, the effective nuclear charge is also increasing. And now the nuclear charge is increasing, and the effective nuclear charge is also increasing, but the shading remains constant. So what it means is that the electrons will be pulled closer to the nucleus. Yes, the effective nuclear charge is increasing. Why? Shading has remained constant, and the nuclear charge is increasing, and the effective nuclear charge is proportional, directly proportional to the effective nuclear charge. So effective nuclear charge is increasing, and shading remains constant. So electrons will be pulled strongly, or stronger, or nearer to the nucleus, thereby decreasing size. So across a period from left to right, generally atomic radius decreases from left to right across a period. Why? We use these two terms. Effective nuclear charge is increasing, but shading remains constant. So it means that lithium will be larger than beryllium, which in turn will be larger than boron, and boron will be larger than carbon, as in that order. So that is it. Across a period from left to right, atomic radius decreases. Now let's look at within a group or down in a group, the trend, whether it's going to increase or whether it's going to decrease. Let's take the group 1. The lithium, sodium, potassium, rubidium, cesium, and francium. Though, as you are moving down, nuclear charge is increasing. So we expect effective nuclear charge is also increasing. But the problem is, as electrons enter into new shells, they go into new principal quantum shells. And if you remember, I told you that the principal quantum number on the average gives the relative distance of the electron from the nucleus. So as electrons are entering into new shells, they are moving far away from the nucleus, and more electrons come into shell. So here within a group, core electrons will increase because more electrons are being added, and electrons which are being added are now entering into next or principal quantum numbers, that principal quantum shells that are far away from the nucleus. So though effective nuclear charge will increase, but the kind of increase in the shielding is greater. And we see that within a group or down a group, atomic size or radius increases. So down a group, atomic size increases, but across a period, atomic size decreases. So let's take this one down. So that is it. Thereby decreasing the size. So across a period, we expect a decrease in atomic size or atomic radius. So we'll have time to look at the trend of the atomic radius down a group. Today, I believe we'll end here, and we'll continue in our next meeting where we look at whether the atomic radius is going to decrease or increase, and the reason for that. The reason why I'm saying that atomic radius increases within or down a group. For the across a period, we have done that. And I hope you are following me. I hope you understand why atomic radius decreases across a period. Because of these two things, these two terms, the shedding effect and the effective nuclear charge. So let me do some quick revision of what we have done, recap of what we have done today. We started with the position of the hydrogen, and I said that hydrogen can be placed in two groups, but traditionally it's placed in group 1 because it has one electron in the outermost shells, and it loses this one electron as the group and we heard that it can also be placed in group 7A or group 17 because it sometimes, or it can gain one electron as the halogens also do. And then we look at the periodic law, where I said that it says that the properties of the elements are the periodic functions of the atomic numbers. In other words, it says that certain properties do occur or do recur at regular intervals. And we also said that the periodic property, which I said is any property which changes periodically in the periodic table, on the periodic table. And then we took some of the first one. Because of time, we couldn't continue on. By all means, continue from here.